All right, here the recording in progress. So here we go. Right, so we're at here. We're doing 3.4, which is on rational expressions, and it's a pretty tough subject, no question about it. So we'll see what we can do about it. A quick word about the quiz. So you should have gotten an email back from me about the quiz. If you did not, let me know. As always, quizzes are out of 5. So the quiz, you got 5, 4, 3, 2, 1, or 0. And I sent out solutions, I think, Saturday morning. Usually the next day, you know, if something's due on Friday, like a quiz on Friday or a test on Friday, then I give you the video next day. So you should have gotten a video on how to do the quiz in case you didn't catch that. Okay, so if you didn't get an email back from me on the quiz, then let me know. All right, and another quiz this coming Friday, and then the Friday after that is our third test on the 8th. Okay, a lot of buffer days because we need it, especially for this rational stuff. This section's somewhat challenging. And it's one of the harder topics in calculus also. So when you get to calculus, you'll see some more of these, and you'll be graphing such things also. Okay, so let's try to dive right in. So we're here, done with this and this, 3.41 to 43 odd. Okay, and yes, the next test only, quote unquote, covers these 5 sections, but that's a big only. I mean, 3.4 is a pretty big section, as it were. Okay, looking much ahead, this is all trig. It's a review of trigonometry. It looks like it's our biggest chapter, and it is. So we'll take quite a bit of time to review our trig. And then it looks like the last 2 tests don't cover that much material either. So we'll see what we can do from here. Okay, so back to 3.4. So I'll be jumping here and there about some problems. Okay, problem 17, f of x equals 3 over x minus 2. All right, so let's get the asymptotes. The vertical asymptote, you can tell right away, x equals 2, because x equals 2 is not allowed. So it automatically gives me a vertical asymptote. Okay, now, I should hasten to add, just because you see something in the denominator like this, like x minus 2, doesn't automatically make it a vertical asymptote, because you might have an x minus 2 in the numerator also, which would cancel it out. And we'll see examples of that. Okay, but here, there's no x minus 2 on top that's going to cancel it out, right? So x equals 2 becomes an asymptote. So whatever else the rest of the graph looks like, there's got to be an impenetrable barrier right here, right? Like, stop. You cannot cross this asymptote, right? And the logic behind that, why cannot I cross? Well, if I cross x equals 2. That means you would have a point 2 comma something, but you already know you cannot have 2 comma something, right? So, and you tell from the final graph, right? There's nothing like that. There's nothing like that. So this seems consistent with what we already have. Okay, so VA, vertical asymptote, x equals 2. Horizontal asymptote, you can consider n behavior. Okay. Well, this is pretty easy. If you plug in a super big number, 1,000,000, this is almost 0. If you plug in a super big negative number, this is also almost 0. So they go toward the x-axis. So horizontal asymptote, y equals 0. See, I didn't really plug anything in. I don't have to. If I say 3 divided by super big, 0. 3 divided by super big negative, still almost 0. Okay. So again, I'll abbreviate vertical asymptote with VA, horizontal asymptote with HA, as it were. Okay. All right, then I consider what happens when I get really, really close to the asymptote from the left side and the right side. That'll either tell me it's going to go to infinity or negative infinity. Okay. It either shoots up or it shoots down. So x approaches 2 from the right. That means plug in a number like 2.1. 2.1 minus 2, positive. Positive divided by positive, positive. Y approaches infinity. Shoots up like that. How about x approaches 2 from the left, like 1.9, 1.99? Well, 3 divided by 1.99 minus 2 is a negative number. So I approach negative infinity. So there we go. There's that. Okay, the text also asks for intercepts, I believe, so intercepts should not be that bad. Find any axis intercepts. So remember, x-intercept means y equals 0. Y-intercept means x equals 0. Maybe I'll emphasize that again here. X-intercept, y equals 0. Y-intercept, x equals 0. So just plug in x equals 0. 0 comma negative 3/2. So there it is.
On tests and stuff like that, like how many points would you like? Can we just have 1 point on there?
You mean for the intercepts? Yeah, there is only one, so you have to.
Well,
have
yeah.
one.
I get that. Oh,
Yeah,
so
there's
that's
no
an
other point you
intercept.
can
Yeah.
put down that would work.
Okay.
Yeah. Now let me explain this a little. That might be a little bit different. When y is 0, notice I cross it out. Y cannot equal 0 here. If I take a, by the way, I say y. Where's y? Well, f of x is y, right? If I put a 0 here, that's impossible. 0 equals 3 divided by, maybe it's better to just cover this up. 3 divided by what number gives me 0? That can't happen, right? The only way that a fraction can be 0 is if the top is 0. Right? But the top's already 3. So this is impossible. Right? So 0 equals 3 over x minus 2. That can't be done. Like another way you can clinch that for sure is to multiply both sides by x minus 2. You cancel this out and you get a contradiction. You get 0 equals 3. And of course, that's not possible. Okay. So y equals 0 is not possible. So there's no x-intercept. The graph never touches the x-axis. It does touch the y-axis at 0 comma negative 3/2. Okay. All right, so that's it for that one. 21 is a much harder problem. There's a lot more stuff going on, unfortunately. So 21, f of x equals blah, 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 all that stuff. All right, first thing to notice in terms of finding asymptotes. If I were to multiply this all out, I get 2x squared plus blah, 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 right? If I multiply all this out, I get 3x squared plus blah, 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 blah. Now, if these two are of the same degree, they're both second degree, or if they're both third degree, or if they're both fourth degree, or whatever, same degree, the rule for the asymptote is y equals the ratio of the leading coefficients. Okay? In other words, you just ignore all the rest of the stuff. Yes, there's going to be an x term, there's going to be a constant. You just ignore it and just look at this. So y equals 2/3 is my horizontal asymptote. It's as if to say, when x is super big, all these other terms drop into insignificance. The x term lags way behind, the constant lags way behind when you have this. If I plug in a billion, this dominates this completely. Okay, this has some x, has some number, we don't care what it is. This is going to be way bigger. So if I plug in a billion, right, you got a billion squared, this might be in the order of a billion, it's way smaller. Now, try to teach you this thing, it sounds weird. I mean, most of the time you think of a billion as a pretty big number, but a billion squared is way bigger than a billion. In fact, it's a billion times bigger. Right, so a billion squared is way bigger than a billion, the same way that a billion is to 1. Okay? So if I were to say, you've got the number 1 and the number 1 billion. Well, 1 billion is 1 billion times bigger. Well, likewise, 1 billion squared is 1 billion times bigger than 1 billion. It's like 1 billion squared looks at 1 billion and say, man, you're puny, you're really small. Just the same way as 1 billion compared to 1, you say, oh yeah, 1 billion is way bigger than 1, right? So what I'm trying to say is that when you get something like this, if they're the same degree, you just have to look at the leading coefficient. So in other words, it's essentially 2 times 1 billion squared divided by 3 times 1 billion squared, which is 2/3. So y equals 2/3 will be a horizontal asymptote. Y equals 2/3. Okay, so again, you just take the ratio of the leading coefficients if they're the same degree. So same degree. So what if they're not the same degree? Then we do something else. Well, like over here, they weren't the same degree. This is degree 0. This is degree 1. Okay, the bottom wins, so the ratio ends up being 0. All right, so how to end up with all this mess here? Okay, so horizontal asymptote, y equals 2/3. Vertical asymptote. So set each of these equal to 0. That's x equals 3. This one, a little bit of algebra, you would subtract 1 divided by 3, x equals -1/3. So x equals -1/3 and x equals 3 are vertical asymptotes. So x equals -1/3, x equals 3. So ignore the red lines right now. I got my asymptotes. Y equals 2/3 up here, and then that's horizontal. Vertical, x equals -1/3 and x equals 3. Okay, and what about all the other stuff? Okay, let's get the intercepts. Plug in x equals 0. Put a 0 there, 0 there, 0 there, 0 there. Well, you get -1 times 2, -2. 1 times -3 is -3. So -2 divided by -3, 2/3. So 0, 2/3. Graph touches the y-axis right there. X-intercept. Excuse me. Y equals 0. If y equals 0, well, that means the numerator is 0. Okay, a fraction is equal to 0 when the numerator is 0, right? So what number makes this 0? -2. This one, do a little algebra, you can figure it out. It's going to be a half. Okay, so I have 1/2, 0, -2, 0. All right, so these 3 are my intercepts. 0, 2/3, 1/2, 0, -2, 0. By the way, this itself almost tells me that it's probably going to go like that in the middle section, right? You got an asymptote, touches here, touches here. So the most likely scenario is it goes up here and it goes down here. But we're going to verify that with our sign chart. Okay, so when I go out toward infinity, I approach 2/3. When I go out toward negative infinity, I also approach 2/3. Okay, so back here, if I plug in 1 billion, this fraction is almost 2/3. If I plug in -1 billion, the fraction is also almost 2/3. Now, what about in between? So I need to determine what happens when I'm near the asymptotes. A little bit to the left of -1/3, a little bit to the right of -1/3, a little bit to the left of 3, a little bit to the right of 3. Okay, I think I'll do the 3 first because it might be a little bit easier because they're like positives. So the expression is right here. Okay, I can't really show you both at the same time unless I make this smaller. Okay, I'm not sure if you can see this. Well, I think I'll just keep it bigger and come up and down. Okay, x approaches 3. The plus means from the right. 3.1. Okay, I know what I do. I'll just look at the sign chart and go from there. Okay, they're all positive. Let's see if that's true. 3.1. Positive, 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 positive. They're all positive. X approaches 3 from the left, 2.99. Okay, it looks like the only one that's negative is this one. Let's try 2.99. 2.99 times 2, that's positive. Don't care about the exact value. Positive, positive. Aha, 2.99 minus 3, that's a negative number. So negative. Okay, well, over here, it doesn't even look like I filled out the chart. So a little bit to the right of negative 1/3. Well, a little bit to the right of negative 1/3 is like 0. All right, maybe that's why. Yeah. 0. 0 gives me 2/3. So positive. So I just directly plugged in. A little bit to the left of negative 1/3, negative 1. So I got this sign chart for negative 1. The only positive is the upper right one, negative 1. Negative 1 plus 2, positive. But negative 1 here, negative. Negative 1 here, negative. Negative 1 here, yes. So it looks like I have this sign chart. 3 negatives means negative. All right, negative means y approaches negative infinity. Positive means y approaches positive infinity. Negative infinity, positive infinity. Okay, so here we go. To the left of negative 1/3, shoot down to negative infinity. To the right of negative 1/3, positive infinity. And then the analysis of 3. A little bit to the left of 3, negative infinity. A little bit to the right of 3, 3.1, positive infinity. Over here, end behavior goes toward 2/3. End behavior here goes towards 2/3, has to touch this. So there's the graph. Shoots like that, and like that, and like that. So you can see it's kind of tricky. A lot of interesting stuff going on here. Okay, 25 is kind of interesting. That's a little different. X squared plus 2x minus 3 over x minus 1. Yeah, here's an instance where you might say, oh, sure, x equals 1 vertical asymptote. Not so in this case, because if you factor the top, x minus 1, x plus 3, before they back out to check, x squared plus 3x minus x plus 3. Okay? And x minus 1 cancels out. So I have x plus 3, but since this was still the original equation, I still need to say x is not equal to 1. Okay, so again, back in algebra, when we did these simplifications, we're actually a little bit sloppy. To say this is equal to this was not really true. I even gave you a problem like that on the test and the homework, right? Where it said something like, oh, what's the difference between this one and this one, right? I forgot what the exact problem was. But let's say this was the question on the test, right? What's the difference between this and this? The answer was x equals 1 is not defined here, but x equals 1 is defined here, right? Remember doing something like that on the test? Okay, most of you got it right. Okay, so the only difference between this and this is x equals 1 is not okay here, but it is okay here. Yes, question.
What is the difference between that and on 21, how it goes through the asymptote, yet we include it, yet it is included?
Okay, so over here, I had no cancellation, right? Basically, there was nothing to cancel here. I'm showing you this case, there is a cancellation. X minus 1 cancels out. So you don't have an asymptote. You still cannot cross x equals 1. That's still true. If you look at the final graph, x equals 1 isn't allowed. But it's not going to be an asymptote. because we can cancel the x minus 1. All right, so what we're really trying to say is that what does y equals x plus 3 look like? Well, that's a line, mx plus b, right? Slope of 1, y-intercept of 3, but x is not allowed to be 1, so I punch a hole at 1, 4. Okay, so again, this and this are almost exactly the same. They are the same everywhere except at x equals 1. So in your Algebra 1 class, when you did stuff like this, right, you said, oh, this is equal to this. Not really true. It is true for all real numbers except for 1. Because 1 is allowed here, right? You can plug in 1, 1 plus 3 is 4. But 1's not allowed here because you're dividing by 0. So this graph has a hole in it. So there's no ha or va, no horizontal or vertical asymptotes. You say, how do you know? Well, x plus 3 is a line. It just goes like this. And I throw out the point 1, 4, because 1 gives me 4 here, but that wasn't the original question. The original question is this, and x equals 1. I don't get 1, 4 here for sure. So it's as if to say, you've got this line, and I just kind of get my punch a hole at 1, 4, and everything else stays the same. So that would be my graph of this. And they also ask for intercepts. Well, you can tell from the graph 0, 3, and -3, 0. Probably easy to look at this. You can sneak in a y here. Put in 0 for x, y is 3. Put a 0 for y, put a 0 here, then x is -3. So -3, 0, 0, 3. Here's the line, except I punch a hole at 1, 4. So this is the graph. Okay. So that's the way that one works. Okay, next one I was going to show you is 29. And 29, we do not have equal degrees. Whoops. Yeah, 3x minus 2 over x squared plus x minus 6. Okay, the top is first degree, the bottom is second degree. So the denominator has a higher degree. Can we factor the bottom? Sure. X plus 3, x minus 2. Can I cancel anything on top? No, we cannot. These don't cancel. 3x minus 2 isn't going to cancel x minus 2. Now, if this was x minus 2, whoops, over here, x minus 2, then I'm going to take this x minus 2 and cancel that x minus 2, and the problem will be kind of similar to this one. But obviously, you cannot cancel here. So these will give me my 2 vertical asymptotes. So va, vertical asymptote, x equals -3 and 2. Okay, how about ha, horizontal asymptote? Okay, first degree, second degree. The degree of the denominator is greater than the degree of the numerator. When x gets super big, either positive or negative, the bottom's going to win, so to speak. It goes to infinity much faster, so the ratio turns out to be 0. Or again, you can just look at the leading terms. For super big x, ignore this and ignore that. It's basically 3x over x squared. I mean, plug in a billion. 3 billion minus 2. 3 billion minus 2 is still 3 billion. Right? Theoretically, if you got 3 billion of something, if you have $3 billion, you should not stress over losing $2. Right? Okay, you still basically have $3 billion. If I plug in a billion squared is way bigger than a billion and a -6. Just ignore it. So we have this. 3x over x squared, x's cancel out. It's just like 3 over x. Well, 3 over x goes to infinity, the ratio is 0, right? So y equals 0 becomes a horizontal asymptote. Again, if I plug in a super big number, this is in a neighborhood of 3 billion, but the bottom is billion squared, which is way bigger. That's almost 0. Same thing if I plug in a negative. If I plug in negative a billion squared, the bottom still is much bigger in absolute value. So the ratio is 0. So VA, vertical asymptotes, -3 and x equals 2. Horizontal asymptote, y equals 0. By the way, I am picky about putting the x equals or y equals. I will take off points if you don't put it. Okay, so if you just put -3, 2, and 0, that's not good enough. I will take off points. A vertical line, remember, has the equation x equals something, or horizontal line has the equation y equals something. So you should put that down.
I thought I'm a little confused. I thought the horizontal asymptotes is what made the top 0.
So horizontal asymptote,
Yeah.
if you set the numerator equal to 0, that will give you y-intercepts. It'll give you intercepts,
No,
but it
what
doesn't give
made
you
the
asymptotes.
top 0? Like what 3x minus 2? What makes 3x minus 2 equals 0?
Correct. So that would be x equals 2/3. So 2/3 0 is an intercept.
Oh, okay.
That's different than an asymptote.
Okay, all right, yeah, I know that makes sense. So wait, how do you find again the horizontal asymptotes?
Right. So horizontal asymptote, that's end behavior. So we have to ask what happens when x gets big, either positive or negative. Okay. So when x gets super big, plug in a billion, the bottom is much bigger than the top, which means the ratio is 0. If I plug in a billion, the top is about 3 billion. The bottom is like a billion squared. That is way bigger. It's bigger by about a billion times bigger. Which means the ratio, if I take this divided by that, it's almost 0. You don't need to punch it in a calculator. I want you to think it out that the bottom is way bigger. So if I divide, I'm going to get practically 0. So y equals 0. So on both the left and the right sides now, if I plug in negative a billion, the same logic applies. Okay? This thing approaches 0. It's like the denominator wins for super big x. The denominator is much, much bigger.
I see. Thank you.
Okay, well. All right, asymptote. Y equals 0. Vertical asymptote, x equals -3, x equals 2. It doesn't cancel out. Okay, so asymptote here, -3, +2, and y equals 0. It's the same thing as saying the x-axis. And yes, I have these points, 0, 1/3, very crudely there, 2/3, 0. Yeah, that itself almost tells me right away that, you know, the graph is going to probably go like that and like that, but we'll double check each side. Okay, introduce another notation. When x goes to infinity, y approaches 0 from above. It gets close to 0, but it's positive. Okay, so again, let's play the game of plugging in a billion. Where'd it go? Yeah, here, billion. Positive, 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 right? But the bottom wins. The bottom is much, much bigger. So y approaches 0 from above. So my graph is going to be a little bit above the x-axis. Y equals 0. And what do I have here? X approaches negative infinity. Y approaches 0 from below. I'm a little bit below the x-axis. How do I know that? Negative a billion. Negative, 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 right? Plug in negative a billion. Negative, negative, negative. 3 negatives make a negative. And I already know it's a very small number. So it's going to be slightly below. Like so. Right. Then I do my sign chart. So I take my 2 vertical asymptotes, -3, a little bit to the left, a little bit to the right. The minus sign means a little bit to the left. The plus sign means a little bit to the right. Same thing with 2, which is a x equals 2 vertical asymptote. I go a little bit to the left, a little bit to the right. Okay, so like -3.1. -3.1, they're all negative. Let's check. -3.1, negative. -3.1 plus 3 is negative, right? Negative 3 minus 2 is negative. So I have three negatives. Three negatives gives me a negative. Y approaches negative infinity. Okay, so I'm a little bit to the left of negative 3. I go down toward negative infinity. And on this side, I already know I approach 0 coming from below. If I move a little bit to the right of negative 3, negative 2.9, looks like I'm going to positive infinity. Let's see if that's true. So negative 2.9, here's my sign chart. Let's check. Negative, positive, negative. Negative 2.9. Negative 2.9, negative. Negative 2.9 plus 3 is positive. Negative 2.9 minus 2, that's a negative. So yes, indeed. Negative, positive, negatives. Two negatives makes the whole thing positive. So y approaches positive infinity. So on this side, shoots up like that. And that's what we were guessing was going to happen anyway. Goes like that, touches here, and we suspect that on this side it's going to shoot down, but let's double check. So x approaches 2 from the left. Oops. I don't even think I have the right numbers here. Do I? Oh yeah, I have it. I'm sorry. 2. 1.9. Okay, 1.9 positive, positive, negative. Let's double check. 1.9. Well, it's a little bit hard to. 3 times 1.9 is 5.7. It's positive. 1.9 plus 3 positive. 1.9 minus 2. That's negative. So positive divided by positive times a negative, negative. So y does indeed approach negative infinity. And there we go. And finally over here, something a little bit bigger than 2, 2.1. X approaches 2 from the right. Okay, so 2.1, they're all positive. 3 times 2.1 minus 2 positive. Whoops, over here, 2.1 positive. 2.1 plus 3 positive. 2.1 minus 2. 2.1 minus 2 is still positive. So 3 positives gives me positive, so y approaches infinity. So a little bit to the right of 2 goes to infinity. And end behavior, when I go way out here, we get close to the x-axis. So that looks like that's what we have over here. Okay, so you can see there's a lot of stuff that's going on in these problems. But just kind of break them down, find my intercepts. End behavior, what happens when x goes way out to the left, way out to the right. Okay, and then find your vertical asymptotes, pick a number a little bit to the left and a little bit to the right, and that'll tell you if you're going to infinity or negative infinity. All right, I'm just about done, folks. I was just going to say one thing that doesn't apply to any of the problems we've had so far, but we will later. That deals with slant asymptotes. Let me just introduce the idea of a slant asymptote. Page 164. So far, we've got horizontal asymptotes, vertical asymptote. How do you get a slant asymptote? Okay, if you want a rule, it's right here. The degree of the polynomial p of x is exactly 1 greater than the degree of the polynomial q of x. So the numerator is degree exactly 1 more than the denominator. Okay, I've got my version of it. So what the book has is correct. I'll give you my version of it. We will have a slant asymptote. Sometimes they say oblique asymptote, but I'll just say slant. If the degree of the numerator is 1 more than the degree of the denominator, exactly 1 more. Here's some examples. Y equals 3x cubed over 7x squared. Okay, 3rd degree, 2nd degree. Y equals negative 4x to the 7th plus blah, 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 over 3x to the 6th plus blah, 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 blah. 7th degree, 6th degree, exactly 1 degree higher. Then you will have a slant asymptote. Okay, and problem 37, which I won't do today, but I'll save for next time. This will definitely have a slant asymptote. How do you know? 2nd degree, 1st degree. So the degree of the numerator is one more than the degree of the denominator. So that tells me I have a slant asymptote. Here's the book's version. They have it over here. The degree of the polynomial R of X, degree of the polynomial Q of X, okay, exactly one greater. Okay. Or here's my version of the same thing. So this thing will have a slant asymptote. This is the final answer. I'll show you how we get that maybe next time, but there will be a slant asymptote. However, for like 39, oh, I'm sorry. I don't want to say however. X squared, blah, 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 X, blah, blah, blah. Okay. Second degree, first degree. Once again, we will have a slant asymptote. As you can see right here, there's going to be a slanted asymptote. Because this is second degree, this is first degree. Take a quick look at that. Whoops. Yeah, sketch the graph of the function and label the slant asymptote. Or they're telling you it's a slant asymptote. Second degree, first degree, second degree, first degree. Okay, so we'll see how that works out next time. Okay, I was going to be done with today, folks. So unless anybody has any questions, I'll call it a day. We have started to do, so we've started to do some of the problems in 3, 4. We can take our time. I can do some more Tuesday and maybe even Wednesday. Okay, yes, question.
So you explained to me like how you could tell that the horizontal asymptote was y = 0, but what is the mathematical way, like I'm just like blanking on it right now, to find the horizontal asymptotes in general? Like it has to do with the numerator, right?
It has to do with the numerator and denominator. So
could you just like go through it really quick? Like how, like if you in an equation, like how do you find the horizontal asymptotes again?
Okay, so how do I find a horizontal asymptote? I didn't actually give you a rule yet, but I was going to. But if the degree of the numerator is smaller than the degree of the denominator, like over here, and didn't we do another one? Like here, right? Okay. Then y = 0 turns out to be a horizontal asymptote. So if the degree of the top is less than degree of bottom, you could say numerator denominator, then y = 0 is a horizontal asymptote automatically.
Okay.
Okay, so example is this one. This is degree 0. We would say degree 0, degree 1. The bottom wins in the long run for sure. If I plug in a million or negative a million, the ratio is almost 0.
What about, what about for other cases though?
We'll see other cases. So right now we've tackled degree of the bottom is bigger than degree of the top, and we tackled what happens if they're equal. Okay, but yeah, we're actually not going to consider every single scenario, but these are some, and now we know what happens for a slant asymptote. So the degree of the numerator is exactly one more. So if they're equal, the degrees are equal, then we play this game. I look at this and say, oh, second degree, 2x squared plus blah, 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 3x squared over blah, blah, blah. Y = 2/3 is a horizontal asymptote. Now, if the degree of the numerator is smaller than the degree of the denominator, which means in the long run, the bottom wins, the ratio is 0, then y = 0 is a horizontal asymptote. So y = x plus blah, blah, blah over x squared plus blah, blah, blah. That will be a horizontal asymptote for sure. Or y = I don't know, -3x⁴ plus blah, blah, blah over 2x⁶ plus blah, blah, blah. 4th degree, 6th degree, 6th degree is going to win. So y = 0 will be a horizontal asymptote. In the long run, the ratio is 0, is what we're saying. Okay. All right, any other questions, please? Let me stop share for a moment. Check anything else, otherwise we're done. All right, let's call it a day. All right, everybody, have a good day, and we'll see you next time. Okay. All right, bye, everyone.